Okay, in this lecture, we talk about an alternative procedure or a method to find the solutions, particularly a linear ODE of order 2. Okay? Now, let us motivate ourselves. This is the method which is called power series solutions. So we consider a second order linear ODE with variable coefficient and which is homogeneous. Consider the second order linear homogeneous ODE, look, which can be written in that form. Y double prime plus A1 of X Y prime plus A2 of X Y equal to 0. Okay? Please note the change in our notation, right? Second order good ODE. Please note the change in our notation. We use X as the independent variable. Okay? So in the previous lectures, we often use T, or we denote by T the independent variable. Now we we are looking for a function y which depends on x. As you see, this is the standard form or reduced form of a second order linear homogeneous ODE. Let's say 1, okay? Where A1 and A2 are the two coefficients which are functions of x, okay? Definite functions of x. Or sometimes this equation can be considered in that form. Q of x y prime plus r of x y equal to 0, which is identical to this one. Actually, this is identical to the first form, where we divide both sides by p. So we have q of x over p of x y prime plus r of x over p of x y, which is 0. Okay? So as you see, if we denote the coefficient of the first derivative by a1 of x, we return back to our previous and standard notation when r over p is denoted by a2 of x. Okay? So consider a second order linear ODE of this form or this form, which is non-reduced form. Okay? Now, we know from the theory of linear ODE that this equation has a solution which is valid or which exists in some x interval where the two coefficient functions are both continuous. Okay? Now, and the general solution of 1 is very well known, okay? Or the type of the solution is very well known. It is the combination of two linearly independent solutions. is of the form very well known from the theory of linear differential equations, where y1 and y2 forms a fundamental set of solutions. Good. We mean that the two solutions are linearly independent with this Wronski determinant of y1 and y2 is non-zero, okay, on some x interval from alpha to beta, where the coefficient functions are both continuous. Good. Now, the theory is very well known. The solution is of the form. So we have to find what about y1 of x, y2 of x. So we know that there exist two linearly independent solutions for the second order ODE, and the general solution is the linear combination of them. However, unfortunately, there is no general method to find y1 and y2 in terms of a finite combination of elementary functions. In other words, closed form, or to find closed form, explicit analytical solutions. I mean, writing both y1 and y2, yes, as a finite combination of known elementary functions is not possible, okay? So note that here is the remarks say to find explicit closed form solutions. I mean, expressing in terms of finite combination of known elementary functions, okay, is in general not possible. Okay, although the theory is very well known and the general solution is expressible in that form. So in practice, from a practical viewpoint, the question is to find y1 and y2. And unfortunately, there is no general method to find or to express the two solutions, y1 and y2, explicitly, or sometimes we say an explicit closed form solution, where we mean that a solution which is written as a finite combination of known elementary functions is not possible, okay? Recall that it is possible to find explicit closed form solutions in some cases, okay? Exception okay, is that constant coefficients case. Good. But As you observed, we consider an equation with variable coefficients. Good? With variable coefficients. In the case where we have an equation with constant coefficient, that is a1 y prime, a2 y equal to 0. Recall that we write down the characteristic equation, which is lambda squared plus a1 lambda, a2 equal to 0. We find the two roots and then express the solution in terms of basic trigonometric functions or exponential functions or monomials or any combination of these functions. Okay? But in practice, we often encounter a second order ODE with variable coefficients, and therefore there is no general method to find y1 and y2. Okay? As a function in terms of elementary functions. Okay. Now, another remark is that, look, we consider a second order ODE which is homogeneous. Good? A second order ODE which is homogeneous. So there is no loss of generality in considering a homogeneous ODE. If you recall that whenever the solution of the corresponding homogeneous equation is known, it is always possible to find a particular solution using the method of the variation of parameters. So it is of crucial importance to find the solution or two linearly independent solutions of the corresponding homogeneous equation. So there is no loss of generality to consider a homogeneous ODE. Good. And so finding the solution of that, if we consider a non-homogeneous equation, we can easily find a particular solution to find the general solution of the non-homogeneous ODE. And look, say there is no loss of generality in considering a homogeneous linear ODE. Okay? So if we solve the homogeneous ODE, then if we have a non-homogeneous ODE, we use the method of variation of parameters to find a particular solution as well. Good. And also, you may say that why do we consider a second order ODE? In fact, in practice, we often encounter a second order ODE. So introducing the procedure or this method for the second order ODE is important from a practical viewpoint, okay? Because we often encounter second order ODEs. Okay, so what is the idea? Look, since y1 and y2 are not expressible as explicit closed form solutions in terms of a finite combination of elementary functions, okay? We try to find the power series or Taylor series representation of the two solutions. That is the idea behind power series solutions. So our objective, look, our objective is to find, we construct a Taylor series or power series in many cases, these are Taylor series. Representation of the solution. Yes, that is because both y1 and y2, two solutions, are not expressible in closed form, we try to find their Taylor series expansion about a point x equal to x0. Good. This is an infinite series like a0, a1, x minus x0, a2, x minus x0 squared, and dot, dot. So there are infinitely many terms in such a sum. This is precisely the Taylor series expansion of the solution about x equal to x0. In particular, if x0 is 0, okay, we are looking for a solution like x a n to power times x to power n. In particular, x0 may be 0, and we consider a solution of the type good, which is a0, a1x, a2x squared, dot, dot, dot. So it is a series in ascending powers of x. And this is why a series like that is often called power series. Right? Yes, we use the terminology sometimes. In general, when we expand any function about a point x0, a series of this form is called a Taylor series about x equal to x0. If x0 is 0, the corresponding Taylor series has this form, and which is called Maclaurin series. Okay. Now, two basic questions now arise. How do we choose x0? Okay. And second, we know that a series of that form, an infinite series, makes sense if it is convergent. Right? So how do we find the radius of convergence of such a series? That is, the x interval in which the series is sure to converge. Okay? And therefore, the infinite series makes sense. Good? So we answer these questions later. Now, so look, how do we choose the number x0? Good? Second, how do we calculate the coefficients an in the power series? Good. Is that an x minus x0 to the power n. And most important is that a power series makes sense if it is convergent. Okay? Clearly, if you look at this power series representation of a solution which exists on some x interval according to the general existence uniqueness theory of linear ODEs, clearly look, y of x0, good, y of x0, remember the explicit form of this series, when x is x0, look, every term beyond the first one vanish. So y of x0 is a0. Right? But does the series make sense for any other x values except the other than the point at its center? Remember, the point x equal to x0 is called the center of the power series or the Taylor series, right? So it makes sense at its center. So it is a0. But does it make sense for any other values of x? So we know that for what values of x? Now the question is, for what values of x do or does the power series make sense? In other words, what is the so-called radius of convergence of such a power series solution? That is, look, it is known that power series, okay, has a radius of convergence. Rho is any positive number, okay, not necessarily integer, any real number, so that the interval, what is the meaning of that? Minus rho x minus x0 is between minus rho and rho, and therefore x0 minus rho, x0 plus rho. So for x values between x0 minus rho and x0 plus rho, a series makes sense, such a power series makes sense. It's converged. That is, geometrically speaking, on x-axis, here is the center of the series, x equal to x0. So this is the radius of convergence, if there is any, okay, non-zero. So here is x0 plus delta, and here is the point at x0 minus delta. So if you choose any x lying in this interval, in this open interval, okay, then our series, power series or Taylor series around x equal to x0 makes sense. So it is convergent if there is a non-zero radius of convergence. This is rho, radius of convergence, where that is rho is called the radius of convergence. Okay? Now, from calculus, there are several ways of finding the radius of convergence. For example, you may use the ratio test or any other test to find the radius of convergence. Okay? So I'm going to give a brief review of power series. Okay, so look, from the power series, recall calculus 2, okay? It is known that a power series makes sense when it is convergent, and we require that there exists a non-zero radius of convergence rho such that x minus x0 absolute value is smaller than rho. Okay, which means that for x minus x0 values between minus rho and rho, or for x values on this open interval from x0 minus rho up to x0 plus rho, or on this line, okay, on x-axis, okay, if rho stands for the non-zero radius of convergence, okay, then for any x in this interval of x, this series makes sense, so it is convergent. So let us give a brief summary about a brief review about power series, okay, to remind these in detail. Look, how can we find the radius of convergence or of a power series? Look, let's say a brief review of power series. Okay? So, definition. Here is a definition. We say that, look, as you remember, an infinite series of the form a n x minus x0 to power n, explicitly written a0, a1, x minus x0, a2, x minus x0 squared, okay, is called a power series. A Taylor series, in fact, or in general, a power series centered at x equal to x0, okay? in particular, so first, in particular, at x equal to x0, the series equals a0. So look, put x equal to x0, as you see, every term except the first constant term vanish. So power series makes sense. It equals to a0, which is a real number. Good. Now, at any other point, at a point, say x equal to x1, good. The power series is set to converge. Good. I'm defining the convergence roughly. To converge, the real number, L, say, if, look, we consider first the finite sum from 0 to a big N, an x minus x0 to power n. So in the notation of power series, this is called nth partial sum of the series. Good. And we put x equal to x1. Okay. So I consider the convergence of this series at the point x1. And then when the upper limit of this series, finite series, goes to infinity, look at that. Actually, when you consider this finite sum, which is called a partial sum or a truncated series, okay, the result is always a real number. Good. It is a finite sum of finite numbers. Good. But when n goes to infinity, this sum may or may not exist. In the case when the limit exists, say L, we say that the power series converges to L when x is x1. Good? Or we also say that the power series converges absolutely okay. Also, we use the terminology absolute convergence at x equal to x1 if this limit, this time we consider again the limit of such a truncated series or partial sum, but we take absolute values of the terms. Good. Whenever this limit exists. In that case, if the series of absolute values, okay, converge, has a limit when upper limit goes to infinity, implying the infinite series, we say that our series converge absolutely at x equal to x1. And it is also known that if a power series converges absolutely at x equal to x1 or at some x, then it is convergent at that x. That is, absolute convergence implies convergence, but the converse of this statement may not be true, or it is in general not true. Good? So absolute convergence implies convergence, but the converse of this statement is not true in general. Okay? Now, to find the x values, the set of all x values, or an interval of x in which the power series is convergent, we use, for example, the ratio test. Fortunately, in this lecture, we are not going to use any test to find the radius of convergence of the series solutions of a differential equation, but we determine the radius of convergence from the differential equation itself, not using any test. Look, but to understand the reason why we introduce a radius of convergence, for example, by the ratio test. Remember the ratio test of calculus. By the ratio test, for example. Right? We look at this limit. Limit when n goes to infinity. We look at the ratio of two consecutive terms in the power series. This is the n plus first term in the power series. Look, do not forget, I'm interested in such a series, a n x minus x0 to power n. This is our power series under consideration. So we consider the ratio of n minus first term and the nth term, which is a n x to power n. Good. And which may be written as x minus x0. Good. When we simplify it and limit when n goes to infinity, a n plus 1 over a n. Good. The ratio test tells us that if this limit, the ratio of two consecutive terms, is smaller than 1, then the series is convergent, implying that x minus x0 good must be smaller than this number. Limit n goes to infinity, a n plus 1 over a n. Okay? And this number may be defined by, as you see, this number is a positive number. Okay? It is the limit of a positive quantity. So it may be several cases. For example, if this limit is 0, okay, then rho becomes infinity. So the power series makes sense for all x. If this limit is infinity, then rho is 0, so there is no positive radius of convergence. So the series makes sense only at its origin, in the case, only at its center, in the case of 0 radius, or if it is a finite number, then the reciprocal of that finite number implies that the radius of convergence is a finite number. But in any case, look, we express the x interval centered at x0, okay, in this form, where rho is defined as the radius of convergence. Okay, in this lecture, we are not going to evaluate this type of limits, okay? But now we understand that if x is somewhere in this interval suggested by this inequality, then the power series is sure to converge. Converge absolutely, implying that the power series converges absolutely. Where, as you see in this interval, here is the center, here is the calculated radius of convergence. So here is x-axis, so we have x0 plus rho. Here is x0 minus rho, okay? So for any x in this interval, our series makes sense. So it is convergent to a number, okay? It gives us a number. Good, converge absolutely. When clearly when x minus 0 is larger than rho, okay, the power series is divergent. That is, if you try to calculate the power series at any x outside this interval suggested by the radius of convergence, we found in that way, the series doesn't make sense. It tends to plus infinity or minus infinity, or it doesn't exist as a real number, okay? So we say that the power series is divergent, making no sense, okay? And when x minus x0 is precisely rho, so at the endpoints of this interval, okay, in the interval notation, this is the interval from x0 minus rho up to x0 plus rho, okay? The interval of convergence. Okay? So at the endpoints of this interval, the series may be convergent or divergent. So when we find the behavior of the series at the endpoints, we can find the exact interval of convergence of that series. So the series may be convergent at both two endpoints, or maybe convergent at only one endpoint. The power series is convergent or divergent. Maybe convergent or divergent. These are known from calculus. Okay, and what is the most important for us is that, look, for this interval, for the interval of convergence, or in the interval where the series is convergent, okay? the power series defines a function of x. That is, we can say that we can consider a function, say f of x, which is defined by this series. Okay? So, but this series makes sense only for x lying in this interval. Good? Or probably at the end points, at the boundary points of this open interval. Could give some x. The function value is calculated as the sum of this series. Okay? So the value of the function is the sum of this series which exists. It is a finite number. This function is infinitely differentiable. That is important for us. Infinitely many times differentiable. So we can take the derivative of that function term by term, or similarly, we can integrate the power series term by term. The function, look, this function, the function f of x, so defined, a n x minus x0 to power n, is infinitely differentiable. Okay? Where the series, can be differentiated term by term to yield or to give this. A n or n times a n good, or f double prime. No problem if you write 0, starting from 0. Adding 0 to a series doesn't change its sum. But when n is 0, we have 0. Okay? So adding 0 to a sum doesn't change its value. I'll talk about that later. n minus 1, so differentiation of this series term by term once more. We have x minus x0 to power n minus 2, and so on. So infinitely many times differentiable. Of course, this series, as you see, when you write f of x, look, explicitly it is a0, a1, x minus x0, a2, x minus x0 squared, a n, x minus x0, n, and so on. Look, taking the derivative term by term, the first is a constant, so its derivative is 0. Then a1, then 2a2, x minus x0, and n times a n, x minus x0 to n minus 1. The derivative of the general term. So as you see, the first term vanishes. So you may start the series from 1 if you want. N a n x minus x0 to n minus 1. Similarly, when you take the second derivative, okay, the derivative of the second term becomes 0. So you can start the series, this series, from 2 n minus 1 a n x minus x0 n minus 2. But if you start from 0, look, when n is 0, this term is 0. When n is 1, the second term is also 0. So there is no problem in writing in this way. But usually we start it from 2, we start it from 1, okay? Because of that reason. Now, what is also known? Look, as you see, the radius of convergence of the original series is a non-zero number for some non-zero radius of convergence. We know that the derivative, this series, and this series, describing or standing for the first derivative of f or second derivative of f, have the same radius of convergence. So the radius of convergence of f prime, f double prime, and other derivative is the same as the radius of convergence of the original series for f of x. Okay? Now, we give the following definition. Let us continue the review of power series. Here is a definition. Now, we say that a function f of x, okay, which equals to the sum of its Taylor series in this way, which equals to its Taylor series. Okay? In an interval. Depending on the radius of convergence. Okay? Is called analytic. In that interval. So, for all x in that interval, okay, f of x is infinitely many times differentiable. Okay? And for all x, such that x minus x0 is smaller than rho, okay? F of x is infinitely differentiable Okay? And the result is a convergent power series if f of x is analytic. Okay? Please be careful. I'm not saying that all infinitely differentiable functions are must be analytic. This is not the case. However, if a function equals to the sum of its Taylor series at some x, at all x, in fact, in that interval, then it is called analytic, and such a function is infinitely many times differentiable. And it can be shown that it is infinitely differentiable or differentiable up to any desired order. Up to any desired order. Okay? Second, if you recall calculus, it is possible to show that it can be shown that the coefficients an has the form okay? 1, 2, 3, where a0 is clearly f of x0. So in such a function defined by a power series, a0 is nothing but the value of the function at the center, and other coefficients are calculated by nth derivative evaluated at the center divided by n factorial. So, and this function is clearly infinitely many times differentiable at x0 and at any other x in that interval, okay? Suggested by the non-zero radius of convergence. And recall our terminology. If or when x0 is 0 or power series, the power series is called Maclaurin series. F of x, such a function takes the form, okay, where for this absolute value of x is smaller than rho, and this interval centered at the origin, here is 0, origin of x-axis, rho, so this is x, this is rho, and this is minus rho. Good. So, or x is between minus rho and rho. Good. With an is nth derivative at 0 over n factorial and for 1, 2, and so on. And f of a0 is f of 0. Good. Now, let us recall some very famous Maclaurin series. Examples are very well known. Series, power series, for example, the geometric series. Okay? A few important and celebrated Maclaurin series are, look, the series for 1 over 1 minus x. Good. X to power n. For x smaller than 1, or this interval, this open interval. This is very well known as geometric series. Good. Explicitly, it is of the form 1x, x squared, x to power n, and so on. Good. Or the Maclaurin series for an exponential function has this form. X to power n over n factorial. This is very well known. 1 x over 1 factorial, x squared over 2 factorial, x to power n over n factorial, dot, 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 for all x, or from minus infinity up to infinity in the case where rho is infinity. Okay? For this case, rho is 1. Radius of convergence of the geometric series is 1. The radius of convergence for the series representing e to power x is infinity. Or this one is very well known also, cosine x from 0 to infinity minus 1 to power n x to power 2n over 2n factorial. So first one when n is 0, and then with a minus sign x squared over 2 factorial, then plus x4 over 4 factorial, and so on. Again, the radius of convergence is infinity, so this series makes sense for all x. So it is convergent for all x, for all finite values of x. Again, rho is infinity. Similarly, you may recall the Maclaurin series for sin x, which is of the form 2n plus 1 factorial. So x minus x cubed over 3 factorial, x5 over 5 factorial, and so on. Again, the radius of convergence is infinity. Yes? Now, what else? Finally, we say that it is possible to operate with power series, or operation with power series is important, or some algebraic operations are possible. For example, you can take the sum of two convergent power series. You can multiply a power series by some number, okay, by a constant number, or you can take the product of two convergent power series. So here are some series manipulations. Which are possible. Let us consider two series, a n x minus x0 to power n, for radius rho 1, say, and let us consider another series by with coefficients Bn. With possibly a different radius of convergence, say rho 2, okay? B two convergent power series. Okay? So we consider two convergent power series. The first one has the radius rho 1. The second one has the radius rho 2. Both are power series. Okay? The sum is possible. Sum or difference is possible. Fx plus or minus g of x is a new series. So we take the sum of the corresponding terms with the same x minus x0 with the same power of x minus x0. So we have an plus or minus bn with x minus x0 to power n. So this is a new series with the new coefficient an plus bn or an minus bn for rho for x minus x0 is smaller than rho, where rho is minimum of rho 1 and rho 2. The smallest value, the smallest radius of convergence, okay, is the radius of convergence of the resulting sum or difference series. Or it is possible to multiplication by a constant is possible that is lambda f of x lambda times an x minus x0 to power n, and multiplying by a constant doesn't change the radius of convergence. So still the resulting series has the radius of convergence rho 1. Okay. Here is an important note. F of x can be multiplied by x as well to give, look, now x is not a constant, to give this xf of x. So we have x times this one, x minus x0 to power n. So a little bit care. So writing x as x minus x0 plus x0. Good. And look at that. This is still x. So an from 0 to infinity, x minus x0 to power n. So multiplying this series by x minus x0, we have this one from 0 to infinity an x minus x0 to power n plus 1. Plus, now x0 is a constant, so we have x0 times an x minus x0 to power n from 0 to infinity. So it seems that we get two series, but the two series may be incorporated under one series. Look, where another important manipulation with series should be introduced, which is called the shifting the index. We sometimes use a shift for the index, and we get that. Look at from this series, I write x f of x Okay, so x f of x is written as the sum of two series, but the two series may be written under one sigma sign. Look, actually, we have this series, first series an x minus x0 to power n plus 1. Let us write this series in the form, but let us write the series writing the first term separately. What is the first term in this sum? x0, a0 plus the remaining is a series starting from 1. Good. The first term is written separately. So this is written as x0 an x minus x0 to power n starting from 1. Okay. Now we introduce the shifting shift index. Sometimes we did that. Say n is k plus 1. We introduce a new index or summation counter k. Okay? So when n is, or k is n minus 1. Okay? So when n is 1, the lower limit of the sum, look, k starts with 0. Therefore, I write x times f of x as that from 0 up to infinity an x minus x0 to power n plus 1 plus this constant term x0 a0 and plus. Now the shift with the shifted index, we have x0 a. In place of n, I write k plus 1. So x minus x0 to k plus 1. But k starts from 0 up to infinity. Okay? When n goes to infinity, as you see, so does k goes to infinity. And look, I write this series as 0 infinity an x minus x0 to power n plus 1. Again, we can interchange again from k to n, and we have x0 a0 x0 plus. So we interchange k by n to write x0 a n plus 1 x minus x0 to power n plus 1. Therefore, now the two series are similar, so they may be written under one sigma sign. So we have a0 x0 plus from 0 up to infinity an plus x0 an plus 1 times x minus x0 to n plus 1. Okay? So note that in this case, we say that summation index or summation counter is a dummy variable or dummy index in the sense that you can choose, it has no role, so having no role on the sum. I mean this, if you write, for example, a j x2 power j, j from 0 to infinity, you can change the summation counter without any trouble, a n x2 power n from 0 up to infinity. Good? They are same. Or you can use k from 0 to infinity, a k x2 power k. They are all the same. Actually, as you see, what is the first one? A0 plus a1x dot dot dot. The second one is the same, although we use counter n, but a0 plus a1x dot dot dot. So, and it is same, this series is the same as the second one or first one, a1x dot dot dot. For this reason, we say that the summation counter in a power series is a dummy index. It doesn't have any real role on the actual value of the sum. Therefore, here, look, if I change the index from k to n again, okay, no problem. We have the same series, and we write x f of x as a constant term plus a series of that form. Now, it is possible to consider the product of two power series. I'm not going into the details, but the product of two power series is a new power series. So product of f and g is a new series of the form from 0 to infinity with coefficient x minus x0 to power n for, again, x minus x0 smaller than rho, where rho is minimum of rho 1 and rho 2, where Cn is something like that, is a finite sum of numbers like a n minus k, bk, or if you consider the sum in the reverse order, we can write it as a k, b, n minus k. Okay? So the coefficients of the product series can be calculated in terms of the coefficients of the first series and the coefficient of the second series, something like that. It is not important, detail is not important. But what is important here, look, the concept of, say, analyticity and the absolute convergence. And absolute convergence can be extended to Okay? Complex numbers. Complex numbers. We use this sometimes, complex numbers as well. Good? So if, this, if f of x, a n x minus x0 to power n is absolutely convergent for x minus x0 smaller than rho. Okay? Then the similar series should converge let's say the center is still real, okay? From a n z minus x0 to power n, okay? Z is a complex number, but center is still real, okay? Should converge for this. Good? But the meaning is different. So where Z, real Z plus I times imaginary Z is a complex number, or Z is something like that. A plus IB is a complex number. Now, please be careful. Now, the meaning for this case, look, for the real case, x minus x0 smaller than rho means this interval. As you remember, x0 minus rho, x0 plus rho, okay? Implies the interval. Good? Geometrically, as you remember, this means on x-axis, good? Here is the center. Here is x0 plus delta. Here is x0 minus delta. Good? Rho, sorry. Rho. In that case, for complex cases, now z minus x0 smaller than rho implies the circle in complex plane with radius rho centered at x0, where x0 is still real. So look geometrically, it means this. Let's say real x-axis, imaginary x, or imaginary z, real z. Good? Let's say y is imaginary and real z is x-axis. Here is x0. We choose real, but you can choose it as a complex number as well. So center is still. So what is the meaning of z minus z0? Z minus x0 rho shows the distance from any complex number. Here is a plus ib. Good. And the distance is that z minus x0 is something like that. Say a plus, or let's say z is x plus iy, okay, is x minus x0 plus iy. Good. And z x0 stands for the modulus x minus x0 plus iy, which is the distance from z to x0, and it is x minus x0 squared plus y squared. This is a smaller than rho. Okay? So z minus x0 smaller than rho implies the circle centered at x0, 0 on the real z or x-axis. So it implies this. Good. Circle. This open ball or open ball. Good. And therefore, if we are interested in the real numbers, in the real values, what is here? x0 plus delta again. Here is x0 minus delta. Okay? So, and this shows why the term radius of convergence, why the term radius is used for rho. In general, for a complex, in the complex plane, actually rho stands for the circle, for the radius of this circle. But when we restrict ourselves to the real numbers, to the line containing real numbers, rho is just the distance from x to x0. Now it shows the radius of a circle in which, look, for any z lying in this circle, the series converges for any complex number. This is again rho, sorry, y delta. Okay? Actually, how can you calculate this formula? Recall that. Look at this. Here is x real part, and this is y, iy, the imaginary part. Okay? So you can consider this right triangle. So x minus x0 squared plus y squared from Pythagorean theorem must be smaller than rho. Okay? So we see that rho is actually a radius when we extend the real numbers to the complex numbers.